Okay, let's go to the next next chapter. The next chapter is gonna be um, electromagnetic induction, right? Electromagnetic induction, right? Electromagnetic induction is the process of creating current by the changing of the magnetic field in a circuit, right? Now let's see how we can change the magnetic field in a circuit. Well, we have different ways. We have, for example, the change, right, of the field strength, right? And we again ways to create current by induction. Okay, we have this mainly four ways. We have changing, right, the field intensity, right, or strength, right, changing the area of a loop or the circuit, right, changing area of loop, right. Also changing the orientation, means rotation, rotating, right, the loop, right. And finally switching on and off a switch, right, in a circuit, right, switching on and off, right, a circuit in another nearby loop. Okay, these are the ways that we use to induce a current, create a current by the changing of the magnetic field strength, by changing the area of the loop, the circuit, right, rotating the loop, right, switching on and off a circuit in another nearby loop. Okay, let's explain these sections to see how this current is created. Okay, let's do it. Let's start with, well, this is the hardest one, changing the biggest strength. For example, imagine that we have a magnet, right, north, south, and these are the magnetic lines, right, given the north pole, right. And imagine that moves right down at this velocity. Well, according to this condition, if we take as a reference this conductor, right, this conductor right here. So if the magnet moves down at this conductor, this is a reference frame, the conductor, right, this circuit, right, the magnetic field is increasing when it goes down because the line is getting closer and closer and closer. So the magnetic field intensity strength increases here. So it means that it's also found by experiment that we have a current produced on this conductor, right? And the current is to the, let's say, to the right, or counterclockwise when you see it from the top, right? So we have a current when we change the strength of the magnetic field. Also, we can get the same effect if we move this bar outward, right? We have the same conductor, but in this case, again, we have a change. Every time we have a change, we create something, every time, right? So in this case, we have a change in the magnetic field intensity. So again, as a reference on this, this conductor is a reference. So at this point, right, we induce a current in the conductor, right? So we have a current acting in opposite direction as before. Let me explain this one later, why that happened. Okay, so we have this situation. Again, every time we have a change, we have something. Right here, we have a change in the magnetic field strength, so we have current. What happens when there is no change, right? Like in this case, right? When velocity is zero. When velocity is zero, right? Current is zero. No current is produced. So current is produced only when we have a change in the strength of the magnetic field. Got it? Okay, great. Now let's go to the next concept, right? Changing the area of the loop. Okay, imagine that we have a magnetic field, constant magnetic field. Magnetic field now goes into the page, into the whiteboard, right? Imagine this is the magnetic field. Usually we take, in this case, the magnetic field to be constant. And imagine we have a conductor here, and we have another conductor. It touches this one, but it's light. On the first one, it has some velocity v. When that happens, right, we're increasing the area. If we increase the area, of course, we are inducing a current, right? So when that happens, we induce a current into the circuit, right? I'll explain this one later, what is happening. And another one, the next one, rotating the loop, right? Here we have a magnetic field, right? Imagine going, it goes down the magnetic field. We have a loop. Usually the loop is represented by this rectangular, right, wire like this. Imagine, right? Now this is the magnetic field, and this is the loop as an area, right? When we rotate this loop inside of this magnetic field, also current is created, right? So we have current is created, right, when we rotate this loop. And the last one is when we have switch, right, in your house, right? Switch on and off, for example, right? The light, right? The power. So we create also a current if we have a circuit nearby, right? So we can see that current is also produced in the next circuit. Okay, great. Now let's go in more detail for this concept. We explained already this one. Let's go to the next one, right? And let's see how is that current. Actually, what is produced is a electromotive force or voltage. Okay, let's do it. But before that, let's go to the concept of the magnetic flux, right? Magnetic flux. The symbol is phi, right? B, that's the magnetic flux notation, usually. Okay, let's see. Flux means just flow, right? We have a flow of magnetic field, let's say. Imagine that this is the constant magnetic field, and now we're supposed to try to catch, right, this magnetic field, right, or make this magnetic field pass through an area. Imagine this is the case. We have a funnel right here, right? If we increase the area of the funnel, we increase, right, the field collected by this funnel, correct? Perfect. So we can say that the magnetic flux is proportional to the area, right? Now, when we're dealing with areas, usually we designate, especially when dealing with surfaces of contact, like when we're dealing with Newton's laws, right? When we have forces and we have an object, right, on this surface, we say, well, we have a normal force, right? Normal force, that is the force acting by the surface on the object, right? So it's very common to find in physics this idea, this concept. Every time we have a surface or area, right, and we can designate, right, or apply a force or a quantity that is important, that is related, right, to the object. Okay, the same thing happens right here. we have an area, right? Any area like this. So we can designate this area, right? And this was a vector, has magnitude, has direction. Like in this case, right? This is like in this case, right? This is the magnitude, and this is the direction. We can rotate, right, the area in this way, and it behaves as a vector, right? It has magnitude and direction. Let's do that concept that helps us to explain the, right, what is happening right here. Okay, so imagine that we have an area in this way. This is the direction of the area, and this is the direction of the magnetic field, right? When these two are parallel, this direction and this direction, right, we have the maximum, right, collection of the magnetic field going through this area, right? But what happens if we change the angle? Well, less and less field goes through this area, and when these two are perpendicular, right, this is zero magnetic fields going through the area. So then which function gives us that when the angle is zero is the maximum, and when the angle is perpendicular is zero? Well, it's gonna be cosine, right? So phi, the magnetic field, is also proportional to cosine of the angle, right? Now, let's combine these two concepts. So the magnetic flux is proportional to the area times cosine of the angle theta, correct? Now, let's eliminate this symbol. How do we eliminate this symbol? Remember, we need to use a constant, right, to match the unit. Okay, the constant that is used in this case is just the magnitude of the magnetic field, right? So it's gonna be equals to V A cosine theta, right? Okay, so this is again the magnetic flux. This one we have one loop. If we have n loops, right? Well, we just multiply this by n, right? NVA, right? Cosine theta, correct? Now this is a new quantity, right? Now let's find the units for this quantity, the magnetic flux. Okay, so the units are this one, right? The unit. So we have two units. One is Maxwell, right? MX, and the other unit is Weber. One Maxwell is just one magnetic line, right? One Maxwell is just one magnetic line. The relationship between these two quantities is gonna be this one. The relationship is gonna be that one Weber, right, is equals to 10 to the 8th Maxwells. Okay, now let's find again the unit for 5. Well, it's not the unit for 5 now. Using that, let's find the unit for the magnetic field, right? Magnetic field, right, from this formula, right? Look, imagine that this is 1, that's the maximum. Now let's use this quantity right here. It's gonna be magnetic flux, right, divided by the area. Perfect. Now, when we use magnetic flux equals to Maxwell, we use Maxwell, and we use square centimeters, right? In this case, the unit is called Gauss, right? G, Gauss, right? That's the unit of the magnetic field, Gauss. What happens if we use the other unit, right? When we use Webers per square meter, so we call this unit Tesla, right? T. So Tesla just 1 Weber per, right, square meter. So these are the units for the magnetic field, again, Gauss and Tesla. We usually use this one because we use the metric system, right, which is using meters, using kilograms, using seconds. But we can have the relationship between these two quantities in this way. 1 Tesla is equals to 10 to the 4th Gauss. So Tesla is a big unit. Got it? Okay, so we found the units in this way for the magnetic field, right? In general, we use Tesla, but we know Tesla is equals to 1 Weber per square meter. Perfect. Now let's go to the next topic, right? Let's go to the next topic. The next topic is we're talking about, right, electromagnetic induction means that the creation of current by the change of the magnetic field, right? Right, actually the change of the magnetic field. And we found that the magnetic field now is related, right, to the magnetic induction, right, or magnetic flux. Okay, let's see, it's equals to area, remember, B area, right, cosine theta, correct? Okay, now we're looking for the change, in, if we change this magnetic flux, right, means that we have to change all of these three quantities, right? We can change the magnetic field and keep the rest constant, or we can change the area and keep the rest constant, or we can, right, change the orientation, right? So we represent up the ideas right here. So again, we have the change of the magnetic flux is going to be, for example, right, A cosine theta times, right, change of B respect to time. This is one way how we can induce or create current, right? Another way when we change, right, of course, gonna be in time. In time, this is changing in time, of course, right? In time. We will change again this magnetic induction, magnetic flux, right? In time, we can change now the area, right? These are constant now, right? Let's say B cosine theta, right, changing area, right, respect to time. This is another way, right, is if we change, right, the angle. So gonna be the A constant, and now we're changing the angle, cosine theta respect to time, correct? Okay, the most important for us is gonna be the last one, right? This is the way how we create the AC current, right? AC current, again, is when we have a coil, right, or loops rotating, right, changing the angle inside of a constant magnetic field, right? And the area of this coil is constant. So we are rotating, right, this coil, right, and we create, right, AC. That's the current that we have in our house, right? So it's the most important one. It's going to be the last section today. Okay, now let's see what happens when we change the area, right? When we change the area, and what should be, again, this current produced. By the way, this is related to, it's found that this is the units for this change is just voltage, the units of voltage. So actually this is, again, the voltage that is induced when we change, right, the magnetic field, the strength, or we change the area, or we change the angle of rotation. Okay, perfect. Now let's do it. Again, we have a quantity. Remember, we have a quantity. By another quantity, we create a new quantity. That quantity is named or called EMF, electromagnetic force, right? EMF, electromagnetic, right, force, right, or EMF, electromagnetic force. So electromagnetic force is defined as the change in the magnetic flux respect to time, right? And it's found that the units is just voltage. So this is actually voltage produced when we change the magnetic flux, right, in time. Perfect. Now let's see what happens when we change the area. We try to find this electromagnetic force, right, when the area is changing. Okay, let's do it. Imagine, imagine that we have this constant, right? Remember, when we change the area according to this formula, right? So what do we have? So we have the change in this magnetic flux respect to time is equals to the constant magnetic field, right? Cosine the angle, right, stays the same, right? And we're changing only the area, right, respect to time. Okay, let's do it. So B magnetic constant, the angle is constant. So this is one of the notations for constant, right, magnetic field. The magnetic field goes into the board. Imagine that we have a conductor right here. This is one conductor, and we have another one that is in touch with that one and is light, right, in this direction with some velocity v. Correct? So at the beginning, look at the beginning, this was the position right here, right, and later the position. So we have a change, right, a change in position of delta x. Correct? Delta x. Now let's see. Let's try to find this change, right, which is actually the electromotive force. So let's do it. Let's use this equation right here. So electromotive force is equals to B. What is the angle? The angle between B and the area, right? The angle, remember, this is the area, right? So we have magnetic fields going through the area. So that's the direction of the area, and this is the direction of the magnetic field. So the angle is 0. Cosine 0 is 1. Okay, perfect. So we have actually the electromotive force is just equals to magnetic field times the change in the area with respect to time. Now, let's see how much the area is changing in this process. Okay, let's do it. So imagine that the length of this conductor is L from here to here, right? From here to here is L. How can I represent that? Okay, let me do it right here, right? This is L, the length, right, of this bar, this conductor, right? And what should be then the area? Well, the area, right, is equals to, or the change in area, right, is equals to L times the change in X, right? L times the change in X, that's the change in area. Correct? Okay, great. Now, let's involve, right, let's involve velocity. How do we involve velocity? Because it's present, the velocity must be constant, by the way. Okay, let's do it. So, how these two are related? Okay, how do we define velocity? Velocity is, right, change in actual displacement, right, respect to time. Okay, now from here, what do we have? We have, when we solve for this delta x, right, we have that delta x is equals to, right, v delta t, correct? Okay, now we can substitute this value right here and this one right here too, right? And what do we have when we do that? We have b, right, times what? Times L times delta x, but delta x equals to what? Equals to v, right, delta t, right, divided by delta t. So delta t is cancelled, right? And we have that the electromotive force is equals to B, right, VL, right? It's constant, constant, and constant. So velocity is constant, right? The electromotive force is gonna be constant. Got it? Okay, and this is called the motional EMF. Motional, right, EMF. Correct? This is the case when we change the area. Okay, perfect. Great. Now, let's go back to the idea of this equation, right? Let's go back. It's a very important equation. This is for one loop, right? Again, here we have n loops. N loops. The electromotive force, right, is equals to n, right? Change in the magnetic flux with respect to time. But it's found, right, that this electromotive force, right, has a negative sign because the electromotive force that is induced, or the current that is induced, right, goes in opposite direction as the change of the magnetic flux. For example, look, if we have, let me explain only this sign, negative sign, right? If we have again a magnet moving down at constant velocity, right, actually accelerating, changing, right, and this is that of the velocity, right? And again, let's take this loop as a reference, right, for the change of this magnetic field. Now, because we know that every time we have a current in a wire, right, the current induces a magnetic field, right? The magnetic field, right, is perpendicular to the current, correct? In that way. And the direction is using the right-hand rule, right? If this is the direction of the current, when you curl your fingers, right, that's the direction of the magnetic field, right? This is a magnetic field. Okay, the same thing happened right here, right? We have a changing magnetic field. Remember, changing magnetic field produces a current, right? Imagine that the current goes in this direction. Imagine if the current were in that direction, right? We have current inside of this conductor, this wire, like this one wire, right? In this direction. So we have, according to the right-hand rule, right, magnetic field going this way, right? If the magnetic field goes in this way, this magnetic field produced by the current on this wire, plus the increase of magnetic fields going down because of this magnet increases, right? The intensity inside. The intensity increases, the current increases even more on the wire. If the current increases more, right, we have more magnetic field created by this wire, right? And more, and this current goes to infinity. But that doesn't happen in nature. The current doesn't increases too much, right? The current reaches one magnitude and stops there, right? No more. Means what? Means that the current that is produced must be in opposite direction. Means that the magnetic field produced by this current opposes, right, the incoming increase of the external magnetic field. The opposite direction. That is the symbol for this, or the meaning for this sign, right? Negative sign. This negative sign by itself, right, is called the Lenz's law. Or Lenz's law, right? Lenz's law. Only the sign, but the whole thing is called Faraday's law. Faraday's law. This is a very important law in this chapter. So we have, right, electromotive force is equals to numbers of loops times the change of the magnetic flux. Remember, it could be changing the magnetic field, changing the area, or rotating, right, the loop with respect to time. Got it? Okay, perfect. Now let's go to the next topic, right? The next topic is gonna be, let me see, what's the next topic? The electric generator. Perfect. Electric generator. Oh, before that, let's go to inductance. Let's go to inductance. Let's go to inductance. Okay, perfect. Look, we have a circuit, we have a battery. It's inductance in DC because we're using the battery. Okay, imagine that we have these circuits open, right? And right here we have a coil, right? We call this the inductor, right? And then we have, imagine, a resistor right here, right? A resistor R. Now it's found also by the experiments that when we use this inductor, this loop, right, section of loops, right, and when we close the circuit, at that instant, right, in a very short time, right? This we have a change in the current, because the beginning is zero. The current beginning is zero in the circuit. When we close it, right, the charges, let's say, accelerate, right, from zero to some amount, right, from zero to some final velocity of the current, right. At that instant, we have a change, we have acceleration, right. Remember, every time we have a change in the charge, we have acceleration, right. Uh, we create, in this case, when we're dealing with charges, we create a electromotive force, right, on these loops, right, this coil, right. That's what is happening, right. When we close the circuit, now by a fraction of seconds, right here. So it depends on many factors, but usually it's a very short time, right. Right here, this inductor behaves as another battery. It resistance, right, to the pass of the charges of the current. Why? Because one more time we have a change in the we have current, right? And current induces a magnetic field, right? The magnetic field that is produced, right, must be in opposition, right, to the incoming magnetic field, right? Remember, this is Lenz's law. Because of Lenz's law, right, the current is going to be opposite. And again, this behaves as an acting opposite direction. We have a current acting opposite direction. So this is battery positive, negative. This acts like a positive and negative, right? In opposite direction. Got it? In opposite direction. Yes, opposite direction? Yeah, I think so, right? Opposite direction. Okay, perfect. Got it? And this is called back, right? Back EMF. This lasts for, again, fraction of seconds. After that, right, when we close this one, we have this back EMF for a while. And after that, right, the current is going to be constant through the circuit. Now this behaves as a regular wire, right, with resistance close to zero. Right here also we can say that this behaves as having a resistance, right, having a resistance, or having, right, electromotive force, right, like that. The same idea, right, opposes, right, to that change. After a while, again, we have constant current, and this wire behaves as a regular wire, right? This core as a regular wire with resistance close to zero. Got it? Okay, that's the idea for inductance. We call this the self-inductance. Okay, now let's find the equation that give us the amount for this self-inductance. Okay, let's do it. So we found that we have a change